Thank you very much, Dr. Sada Bela. You need to allow me to disable to share my screen. Please, can you check from your side there? Enable me to share my screen, please. Okay. Okay. Yes. Yes. Thank you very much. I believe you can all see my screen now. Okay. Okay. Thank you very much. I will consider this to be a privilege to appreciate the host, the host of this webinar. I say thank you to you for this invitation to come and share with you certain things within the scope of mathematics. I really appreciate the opportunity. Thank you very much for that. So before me is a topic titled Mathematics, the Universal Language of Science, Engineering and Arts. So I am Dr. Animation Isaac Larry from the Department of Mathematical Sciences, Fluid Dynamic and Survey Research Group, Federal University of Technology, Akure, Nigeria. Thank you very much. Science is a systematic study, and one thing we know about science is that it's a process that has to do with intellectual and practical activity. To some extent, it encompasses the systematic study of structure and behavior. In this case, we only want to study the structure and behavior of certain physical and natural world. In fact, it has to do with observation and experiment, but most times we may not carry out the experiment. In fact, via mere observation, we can actually carry out the intellectual and practical activity. And in summary, we can now refer to science as the ability to produce solutions in some problems domain. In this case, which means that we already have a problem and we are looking for the solution. In fact, in most cases, we can actually guide ourselves with the research question, such that by the time we have the research question, it will help us to know the answer we are looking for. But to cut the story short, we can see clearly now that science, it has to do with intellectual and practical activity. And in most cases, what we are looking for is that we want to understand the particular situation. We want to provide solutions to certain things. That is what science is all about. And what about mathematics? Wow, that is a wonderful subject. We can call it an abstract science. And as you can see on the screen now, there are many figures, but don't be scared with all these things. What they are telling us is that mathematics is a number, and at the same time is a quantity, and at the same time space. So we use mathematics for all these three things. Whenever we have numbers, whenever we want to quantify certain things, whenever we want to describe spaces. So we make use of what is called mathematics. So to some extent, we can refer to it as an abstract science. But to be candid with you, it's not really abstract because it can be divided into two different groups. And that is why we refer to it as a universal language, because in sociology, mathematics is there. In psychology, mathematics is there. In fact, in history, mathematics is there. In fact, in any area of aspect, as you can see in poetry, music, painting, physics, biology, chemistry, all of them in one way or the other, they have mathematics embedded. Why is it? Because the subject is a language. Let me say it again. Mathematics is just like a language, just like English. We use English to communicate our feelings, to communicate our opinion with others. Likewise, we use mathematics when it comes to exchange of number, quantity, and space. As broad as mathematics, it can be divided into two. We have pure and applied. And when we're talking about pure, it's talking about algebra, geometry, and analysis. And one thing about pure mathematics is that it has to do with in-depth understanding of a key area of research. So, which means that whenever we are talking about geometry, analysis, and algebra, please don't let us forget the fact that we are talking about the language called mathematics. In fact, you agree with me in chemistry. They will say in chemistry, I want to analyze certain things. That analysis has to do with number, and that is mathematics. In history, they will say they want to analyze. What are they trying to analyze? They are trying to tell us about numbers. And likewise, almost every area. In fact, in medicine, I will share certain things with you now, which has to do with mathematics. So mathematics is everywhere and it's very general. In fact, in philosophy, mathematics is in philosophy because it has to do with analysis of premises to reach a conclusion. Likewise in logic, so mathematics is everywhere. But whenever we are talking about applied mathematics, we are talking about modeling, we are talking about algorithm, we are talking about simulation. But what is so special about mathematics now is that it has to do with a way to solve problems. Now let's just take a look at the problem very well now. We have what is called scientific method. What is scientific method? It has to do with a sequence of process starting with question. And the first thing now is for us to have a question. And by the time we have a question, don't forget that you are not the first person to have the question. Some people might have answered the question before. That is why the second stage is very important. We need to understand what is the background of the study. What is the background of the question at hand? Because it's possible that there is already a solution to that particular question. And the next thing now is hypothesis and experiment. Hypothesis is where you are just trying to come up with answers to provide solution to the question you've earlier raised. And likewise, experiment. And like I've said earlier, that most times you don't have to carry that experiment. Even through mere observation, we can actually have answers to our question. And the next thing now is for us to reach a conclusion, which is the answer to the research question. Now, let me share with you now. The first research output is a case of medicine. The question here is this: is it possible to deliver drugs into the cerebrospinal fluid for treatment of patients with brain tumors? That is the question. And guess what? There's an answer to it. There was a particular man from Pakistan. It is called Ayab Omaya. He's a neurosurgeon. He's a Pakistani. And he came up with the answer to this question, and he called the answer Omaya reservoir. Now, what is the role of mathematics in this? Mathematics is very important because it has to do with the volume of the substance that will be injected into the brain. Now, in this case now, there's need for us to control the amount of volume of the fluid we want to inject. The fluid must not be too much, and it must not be too small. So that is the role of mathematics in this case now, because it will help us to calculate the volume of the substance to be injected into the cerebral substance, into the cerebral fluid, in order to address the issue of brain tumor. Research article 2 is the case of geology. Recently, they've discovered a well at Jadran X04, and that is Balochistan province of Pakistan. And as you can see on the screen now. But the question now is this: how exactly do we determine the total depth of that well? It has to do with mathematics. Because after drilling, we need to calculate the length at which we can reach the substance, which is called gas. And at the same time, it can help us to know the volume of gas that will be produced per day in terms of barrel. So that is the role of mathematics now. You can't just say that you discover oil in Pakistan. You need to tell us how far. In that case, we are talking about a number which is length, which is 1,200 meters. And at the same time, what is the amount of substance that you can produce per day? And that is actually telling about 7.08 million standard of cubic foot per day in terms of 0.55 barrel per day. And this is mathematics we are talking about in geology. Because they can't just do without mathematics. They need the language of mathematics to communicate with the world that they've actually discovered something precious in Pakistan. And before I proceed, I would like to say special thanks to the government of Pakistan. You are doing something wonderful, and all over the world, we can see the way you are equipping your younger ones to know the history and to know how to take the country, Pakistan, to the higher height. So before I proceed, I would like to say special thanks to all the leaders in Pakistan. Thank you very much for the investment into the world. Now, case 3 now is the case of physics. Sometimes ago, they were trying to look at the time taken for a single particle of light to actually pass through a molecule of hydrogen. In this case, now you notice that we're talking about the time taken, and that is time. And what is photon? Photon is just like a particle of light. Now, in this case now, a particular scientist, a researcher called Seven Grundmann, is a physicist in Germany. He discovered something special, which is history. The question is this: what exactly the time taken for a photon to actually cross hydrogen molecules. In the study, they discover what is called femtoseconds. You know, in this webinar, I only have the time taken, which is in terms of minutes, for the presentation, and at the same time, we know about hour, we know about seconds, we know about microseconds. Is that all? No, that's not all. The research has now let us know that after calculating, we have what is called 247 femtoseconds, which is equivalent to what we have on the screen. And what is so special about this time now? This time is telling us about it's very possible for a photon to pass through hydrogen, and the time taken, it was actually calculated using the language of mathematics. And what next now is that with this new research now, it's now possible for us to calculate the interaction between light and matter. So which means that there's a way light actually interacts with matter. And to cut the story short, we can now say that femtoseconds is 1 trillionth of billionth of a second, and that is the language mathematics is talking about. And then we can call that one. So let's go to case 4 now. Case 4 is in geography, where I'm going to emphasize on the language of mathematics again. In geography, they discover what is called climate change, and we all know that climate change is real. And what is so special about it now? There was a question, and the question was that what should we expect in the year 2070? Should we be talking about unlivable heat by 2070? That's actually the research question. And what is so special about it is that some researchers in the United States, China, Europe, they warn that in the next 50 years, do you notice that 50 years is a real number, is a number that can help us to quantify at that time that certain things will happen all over the world. And the researchers discovered that 3.5 billion people, they may experience a kind of unlivable heat that is not comfortable with them. And what is so special is because the ozone layer may be affected by that time. And another thing is that the study suggests that there will be a kind of extreme heat. And don't forget, when we are talking about heat is a form of energy. And what is temperature? The amount of hotness or coldness. And when we are talking about hotness or coldness, then we are talking about degrees Celsius. And we need numbers to quantify the extreme heat in the year 2070. And one thing about this is that they said that according to their research, that exact number of people is at risk, and this will depend on whether pollutant levels can be reduced, or perhaps we can control the population. But to be candid, we cannot actually destroy the work of our Almighty Allah. If it is the work of our Almighty Allah that our population should grow, and the next thing is for us to learn how to manage the ozone layer, how to really control the temperature. And in this case, you can see now that we need the language of mathematics now to really describe this situation, which is in geography. So under the worst case prediction now, we're talking about 3.5 billion people all over the world in the year 2070. And that actually means that 1/3 of the world's population may be affected by climate change in the year 2070. Now let's talk about another case again, which is in the case of my environmental biology. There is something called the research question between them before the researcher was that how can we destroy polyethylene-based products like mattress, couches, some categories of plastic and foam toys. Now what is so special about this? It was Dr. Otto Bayer who actually called our attention to these things called polyethylene. It, according to them, is the most versatile of all plastic products that was discovered by them. And the point is this: how can we convert it? And don't forget the mathematics. Mathematics is all about conversion. We convert from meter to kilometer. We convert one temperature to another form. So when you're talking about conversion, we are talking about mathematics. So it is just like a reaction of polyol with a disonate or polymetric isokinate along with additive and catalyst. So according to the researcher now, how can we convert this? How can we recycle it? Why do geology? Because they discovered that there's a particular bacteria which can actually feed on this thing called polyurethane, and it will do the conversion. So which means that if in mathematics we can deal with conversion, then bacteria as well, they can help us to do the conversion as well. That is the importance of research and science, because Yeah, now, according to the researcher now, the research was actually carried out in German Elmhorst Center for Environmental Research, which they let us discover that most of these materials, they're actually causing a flood, a kind of pollution. So these are the bacterium now. Look at the bacterium now. So by the time this bacterium, they feed on the polyetherine materials, it will do the conversion from one domain to another domain. So many polyethylene-based products can release dangerous chemicals into the environment because we can't just leave them like that. We need a kind of mechanism, a kind of bacteria to do the conversion from one unit to another. And that is mathematics for us. That is the conversion we're talking about. Now let's take a look at the case 6 now. It's in computer science, where I'm going to use the language of mathematics again. It's actually in robotic science. The question is, do you know that it takes a coordination to move heavy loads like furniture, coaches, machine, and other loads? For instance, we have a chair we want to carry from one place to another. You will not say that we need robots for that. But what is so special about these robots is that it has to do with simultaneous pushing or pulling and reacting based on what your helper is doing. So the idea was conceived by a group of researchers, scientists called Andrew Barth, Yufeng, Lin Chang, and Omar. What are they trying to say? They're trying to let us know what is called fuzzy logic. Fuzzy logic here is a kind of they develop artificial intelligence. What are they going to do? The robots, more than one in this case now, 2 robots or 2 or more, they will work together to move a coach like chair, like a long heavy machine. They will move it from one place to another. And what are they trying to do? They will accomplish the task with little communication as possible among the robots. In this case, it's not as if the robots are communicating with one another, but they are mimicking one another. And that is where we have 2 robots. They will not share their strategy in advance to complete the task. But the question is it possible? Yes, it's possible. It is called genetic algorithm. This genetic algorithm, it has to do with yes or no. And when we're talking about yes or no, we are talking about 1 and 0s. And 1 and 0, we are talking about binary. And binary is mathematical. So with the concept of mathematics now, they can actually come up with 10 or more robots doing what is called cooperative projects. And don't forget that cooperative learning is very important. And now we can have what is called genetic algorithm that will help 2 or more robots to work together. Let's go to research output 7 now. This one is my own personal discovery. It has to do with viruses. Now let's take a look at biological viruses and computer viruses. One thing about biological viruses is that they replicate only inside the cell. And what about the computer viruses too? They also replicate by copying itself into other computer programs. Now let's take a look at again the invisible face of both biological viruses and computer viruses. Both of them, they will not only replicate, but they carry out what is called incubation. And in the case of computer viruses, that one has to do with when you launch a particular application. And some other like that in terms of mutation and self-defense. We have biological viruses and computer viruses. So what's so special now? Let's take a look at each of them. There is a force driving these viruses to perform certain tasks. And don't forget Newton's law of motion, which says that force is equal to mass times acceleration. So if there's a force driving all these viruses, we cannot change the mass. But what about the acceleration? We can actually make the acceleration to be 0. I am not saying vaccination is not a good approach, but I'm telling the whole world now that vaccination is a trivial solution. I'm telling you the reality. What about the non-trivial solution? Non-trivial solution of most especially COVID-19, because there's a force behind it and there's an acceleration. If we cannot change the mass, but rather we can make the acceleration to be 0, then the force will be 0. And when the force is 0, there will not be anything like COVID-19 again. But the question is how do we make the acceleration to be 0? Let's take a look at number 1. Who used the knowledge of virus and biology to design computer viruses? That is the most important thing now. If we can find the answer to who designed that, then we can go to how did the person design it. By the time we get answer to how it was designed, we cannot see now that the next question is that why did you design it? So by the time we can add answer to these 3 questions, we can see that acceleration of the virus will be 0. And when the acceleration is 0, then the virus we give the force driving the virus will be 0. And this will give us a kind of non-trivial solution, because with this now, you know that before COVID-19 there has been other viruses, isn't it? Yes, we have other viruses like Ebola, yes, polio, we have other viruses like that. But there's a force driving this COVID-19 of a thing, and that force is so high in such a way that if we can find answer to the reason to these 3 questions, then we can see that the acceleration will be 0. And when the acceleration is 0, then the force will be 0. Then there won't be anything like COVID-19 again. Now let's talk about math and art now. Art is the expression or application of human creative skill and imagination, typically in a visual form. You know, when we're talking about art, we talk about sculpture. And look at sculpture. Can you see that it's all about geometry? We talk about painting, it's all about geometry. We talk about music, it's all about mathematics. And all these things, what they're trying to do is just to make the world a better place. And I can see it now that there's mathematics in all of them. Now let me explain better now, using the language called Fibonacci Sequence. Fibonacci Sequence is a subject in mathematics that we're all familiar with, and it has to do with sequence. And if you look at a guitar, you will see the same sequence there. And what is Fibonacci sequence? This is the sequence now: 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, and so on. How do we get the successive sequence now? It's very simple. You just need to add the first 2. For instance now, if you add 2 to 3, you have 5. If you add 3 to 5, you have 8. If you add 8 to 13, you have 21. That is Fibonacci sequence. And this sequence here, we can see it in the piano, we can see it in guitar and other aspects. So that wants to tell us that mathematics is a language, it is everywhere. What is the conclusion now? Conclusion now is that we can now see now that mathematics is indeed the universal language of science. It's not only in science, in engineering and in art. We have mathematics in all of them. Number 2, we need to see mathematics as a general. We need to see mathematics that is a general. And that general, that is the nature. An expert in the field, they encourage to pick one part. So that is why in mathematics we have so many experts, so many areas. We have fluid mechanics, optimization, we have fluid solid mechanics, and we have biomathematics and other aspects. So we are encouraging each and everyone to pick one part. And when you pick one part, then you pursue it. Jack of all trades is a master of none. You can't say mathematics is a language and you want to speak all the languages. No, you need to pick one and follow it. Number 3, younger ones should see mathematics as a language rather than as a subject of a course. So we need to encourage our upcoming underlevel students, undergraduate students, postgraduate students to see it as a language and how to speak the language. Number 3, the best way to start a research study is to come up with a research question. When you have the research question, then you follow it and you explore it. Then last one is that researchers should always ensure that the conclusion of the study should not be far from the research question. Otherwise, they should change the title of the research to be in alignment with the research question. I would like to say special thanks to my friend who invited me for this opportunity to share this with you. And at the same time, I would like to say special thanks to the school university management of Yale University for this privilege to share this with you. Above all, I would like to say thank you very much for listening. Thank you very much. Thank you very much. Thanks for the invitation. I really appreciate. Thank you very much. Thank you very much. Okay. Okay. Thank you. Bye.